Hello and welcome to page 4. What I didn't say on page 3 is that versions A and B actually have the exact same problems, just in a different order. So you won't find a separate video for versions A and B. And on this page, it's a little different. You were given instructions to choose any 5 reactions and choose 2, but I'm going to do all of them. And you should be showing stereochemistry where it's actually given or where you're instructed. So you can see that's going to be the first one here. MCPBA is a type of peroxy acid. It's going to make an epoxide out of the alkene, and we want to make sure to keep the cis alkene or the cis stereochemistry consistent with the epoxide. And there's a couple different ways to show this. We could just show this epoxide where those bonds are in the plane, but we would need to show that the 2 methyl groups that are remaining are pushed forward or they're on the same side. And you could show that either with 2 wedges or with 2 dashes, or it could also be appropriate to simply show the epoxide with stereochemistry here. And those 2 methyl groups there. To be even more specific, you could show that those 2 hydrogens are pointed back. So a couple different ways of showing the same thing. The next product, we see that we formed not just any old diol, but a syn 1,2-diol. This is a reaction that requires osmium tetroxide. I like to think about this as the OSO4 hanging out on top of the alkene, and these 2 oxygens add to the carbons of the alkene at the same time. Once again, it's a syn addition. You can use a couple different sets of reagents. The first one that we came across was osmium tetroxide with pyridine. And then in the second step, to remove the osmium, you use sodium bisulfite. You may also see NMO used. That's N-morpholine oxide, N-methyl morpholine oxide, along with osmium tetroxide. And that basically just carries out the same transformation where we get the osmium on top of the alkene, and then NMO plays a role in removing osmium from that alkene. The next one, we have the addition of hydrobromic acid to this compound here, which already has 1 chiral center, and this chiral center is not going to be touched in the reaction. The bromine is going to go to the more highly substituted carbon of the alkene. So let's just start this off. We're going to keep that stereo center fixed, and on one product, we're going to have the bromine coming forward. That is the R center here. And then on the other product, that chiral center that came in that didn't change, or it wasn't part of the reaction, it's fixed. So the other product is this bromine here, where it's pointing back. This is the S center. This is a mixture of stereoisomers, or to be even more specific, we would call these 2 diastereomers. The next reaction, we're going to be adding molecular chlorine over an alkene. This is an anti-addition of those 2 chlorines. Our product, 6-membered ring. Once again, the 2 chlorines added to the opposite sides of the ring. We still have to account for these methyl groups, so we'll put that methyl group pointing back and the other methyl group and the other carbon pointing forward. You could have used alternated like wedges and dashes, so you could have had, for example, this chlorine was dashed, that methyl's wedged, and you could have put this one wedged and that methyl dash. So either one of those is fine. They're both anti with respect to the 2 chlorines. Now, the remaining 3 problems are the alkene problems in the exam, which hadn't showed up until now. And we are looking for a set of reagents here that are going to initially add water. So it's really very similar to acid catalyzed hydration, but the other term for it is this is oxymercuration, and the demercuration is part of that as well. We are going to be adding an oxygen to this carbon here, and that carbon must have been involved in an alkyne in the starting material. Now, the best answer for this would be where it's a terminal alkyne, so it still has 1, 2, 3, 4, and 5 carbons. So the best answer has this being the more highly substituted carbon, and that would give the only product, because this is a Markovnikov addition. Another possible product, not quite as good, but we'd accept it, is that you could have done the same set of reagents, but instead, if you had an internal alkene, that would have put the carbonyl on either one of those. So this would have been one product, but you also would have gotten the ketone product here, where the double bond was in the middle, either one of those two. So once again, that was the hydration reaction. If you want more discussion on that process, that's discussed in chapter 9, and this is where we learn about tautomerization. And not a whole lot of space left on this page. Maybe I'll just kind of clear this out for a second to show you a little bit of what I mean on that. In the first step of that hydration process, we are actually, or sorry, from the alkyne, we are actually adding an equivalent of water across that double bond, or triple bond, to make a double bond, and it makes this functional group that's called an enol. This is in equilibrium with this, what we call the keto form, which is essentially where this proton moves over to this alpha position. It's a type of isomerization reaction. The reason I spend a little more time on that is because we see that in this reaction as well, in the hydroboration reaction to make an aldehyde. Otherwise, hydroboration would give an alcohol. So we know that it must have been, once again, an alkyne here. And really, there's only one possibility, because that's the only place with those two carbons that you could have an alkyne. So we have our benzene ring connected directly to a triple bond, and this is where the initially the OH group goes, but it's really tautomerizes to that aldehyde. So I'll show you real quick what I mean by that. When we go through and we add water across that double bond, this would be the resultant enol, alkene. So it's still has a double bond. One set of pi electrons picked up water, and we have an alcohol on now the end carbon. This undergoes that tautomerization reaction or process to make this terminal aldehyde. And it's not anything to do with that hydrogen, but I just thought I'd show it. And then our last one on this page, this is our wonderful carbon-carbon bond-forming reaction. Sodium amide is a super strong base. It's capable of pulling off that terminal proton from the alkyne. So just to show the intermediate here, so you can see what happens after step 1. This is your acetylide. It is a very, very powerful carbon nucleophile. And this can go ahead and make a new friend with your alkyl halide. So I'm not really doing a great job with the arrow pushing, but if there were a line in between those, that's what would happen. We would have a new bond between the alkyne carbon and the CH2 carbon, and then bromine leaves. So here we have the 1, 2, 3, 4, 5 carbons involved in that alkyne, and then we have 2 new carbons of the or in this case, an ethyl group. And that's it for page 4. Once again, version B stuff is all the same. They're just reordered problems. And we'll see you on page 5. Thanks for listening.